I have a function called f, and for simplicity, let's just make it an increasing function. And let's look at the graph of f along some interval a to b. Alright. So the graph of f looks something like this, where this endpoint is a f of a, and this endpoint is b f of b. Now what I want to look at right here is this expression f of b minus f of a. What is that? That is the difference between the two y-coordinates f of b minus f of a. Or in essence, f of b minus f of a is basically the vertical distance between these 2 points. So what I'm going to do right here is I'm going to draw an arrow to represent that vertical distance. The vertical distance from this point up to this point, f of b minus f of a. Right. And now what I'm going to try to do is I'm going to try to split that vertical distance. So first let's split this interval. Let's just split this interval into 8 equal subintervals. Actually, we could choose, in general we would split it into n subintervals, but for now let's have n equal to 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 9. Here then. Alright, and then so consequently we split this curve into 8 little pieces. Right? And then one thing that popped out to me at least is that if we look at the vertical changes from each of these like consecutive points, right? So the vertical change from this point to this point, if I represent it with an arrow right here, right? The difference between these two y-coordinates, and then this vertical change, and then this vertical change, and 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 this one, all 8 of them. If we add all of those changes together, we should get the total change from a to b, f of b minus f of a. If we add all of these little arrows, then we should get this giant arrow right here. That makes sense. That should make sense at least. So now let's zoom in. Let's choose one of these points. Let's look at this point, for example. Let's call this one x, f of x. And let's zoom in on that point specifically. Alright, so let's say this is the point that we're looking at, x, f of x. And this is the next point, right? This is so this is one subinterval right here. And this is the next point. And so we have the vertical change up from here up to this point. And I'm going to call that vertical change delta y. Alright, and let's also look at the horizontal change, or at least basically from here to here, that's the length of the subinterval, which is constant for each of these subintervals. I'm going to call that delta x. Alright, and now what I'm going to do is I'm going to draw the tangent line at x right here. So the tangent line should look something like this. Right, and its slope is the derivative. The slope of this line is f prime of x. Alright? Now what I want to do is I want to look at this vertical change. So if we look at right here, we look at this vertical change. That would be like predicted by the line basically, and compared to delta y. Alright, so this vertical change is equal to f prime of x times delta x, right? And this is approximately equal to delta y, right? So let's look at this again more closely, what I just did. So what we're saying is the slope of this line is f prime of x. So if we go across delta x, then the line would go up f prime of x times delta x, because f prime of x is the slope. And this line doesn't go through this point, but it comes really close, and we can say that delta y, this vertical change, is approximately equal to basically the increase that the line went, f prime of x times delta x. Alright? So I hope that made sense. Now what I'm going to do, let's see. Now what I'm going to do is I'm going to draw a rectangle. Right? Well, just a rectangle right here. And I'm just making a rectangle, just a rectangle right here. And I'm making it such that its base is delta x and its height is f prime of x. And the reason I did that is so that the area of this rectangle, this not very well drawn rectangle, is f prime of x times delta x. So the area is f prime of x delta x. So this area, therefore, is approximately equal to delta y, at least. Right? And so just think about it. It's just a imaginary rectangle, a rectangle that I just built right here, just so that it would have an area. I just made it arbitrarily, just like that, so that it would have an area that would be approximately equal to delta y. Its area would be approximately equal to this number, delta y. Right? And now what I'm going to do is I'm going to construct such a rectangle for every single point along this curve. So let's just say this rectangle represents the rectangle with an area of this delta y, this first one. And then now we have a smaller delta y, it's a little bit shorter rectangle, and then we'll have another shorter rectangle, and then a very short rectangle, even shorter rectangle, then we'll have a longer rectangle. 1, 2, 3, 4, 5, 6, 7, 8. Right, and all of these rectangles have the same base, delta x, and all of them have a height of f prime of x. So I made each of these rectangles, and the thing about each of these rectangles is the area of each of them is equal to each one of these delta y's, each one of these arrows. Right, that's the way I built them. I just built them so that they would have an area approximately equal to delta y. So if I sum up the areas of all these rectangles, that's like summing up all of these delta y's, approximately. The total sum of the areas of all these rectangles is approximately equal to this total vertical distance, this f of b minus f of a.